Okay, so let's just recap a little bit by looking at what the gradient of a straight line is. So the gradient m is simply the difference in the y values over the difference in the x values. Yeah. So if we go to the question that we've got there, y equals x squared, instead of looking at those general points, let's consider if that's the point 1, and we'll call that the point 3. Yeah, so if I substitute 1 in, I get the point 1, 1. And if I substitute 3 into x squared, I get the 0.39. Yeah. So if I want to work out the gradient of the line joining those 2 points, it's still rise over run. So the gradient will be equal to the y values, 9 minus 1, over the difference in the x values, which is 3 minus 1, which is just 8 on 2, which is equal to 4. So that's the gradient of that line. All right. So what I want to do is really talk about how I could perhaps write those points in slightly different notation. So what if instead of putting the 0.39, I put the 0.3, and well, how did I work out 3? I substituted it into x, didn't I? So that's f of 3. And that point there is the 0.1, f of 1. So really then my gradient could easily be f of 3 minus f of 1 over 3 minus 1. Again, it's just the gradient of my line. So what if instead of looking at the points 3 and 1, I pick just suitably small points or suitable points. So I've got these general points here. I've got these points here, a squared, some other point a plus h, so a plus a little bit, which would then leave me with the point a plus h squared. Okay, so then the gradient of this line would be equal to, let's do the y values in green. Yeah, because then the gradient of this line would be that y2 value minus the other y1 value over the x2 value minus the other x value. So then if I just expand my terms, a squared minus a squared is 0, 2ah over 2ah plus h squared, if you like. If I take a factor out of this line there, I could have h out the front of 2a plus h all over h. The h's cancel, and I get left with 2a plus h. All right. So in this case here, so that's the general rule for the gradient of that particular line. Okay, if I'm picking any point A. So if my example here, how does that 4 equate to that 2a plus h? Well, for our example, we had a was equal to 1, and the other x value was at 3, which was equal to 1 plus 2, isn't it? So 2 is my step size, or h. So the 2a plus h in our case would be 2 times 1 plus 2, which is equal to 4, which is what we got there. What if I picked a second point? What if I tried another point instead? Call it PQR, and we'll call that, and we'll give that point the coordinate 2, and if I substitute 2 in, I get the point 24. Well, then my gradient m would be f of 2 minus f of 1 over 2 minus 1. F of 2 is equal to 4 minus 1 over 2 minus 1, which is equal to 3 over 1, which equals 3. How does that compare to my general rule? If m is equal to 2a plus h, what was my a value? It was still 1, but my step size h this time was also 1. So my a value was x equal to 1. My next a value, if you like, was x equal to 2. So if I put those values in, I get m equal to 2 times 1 plus 1, which is equal to 3. Okay, so what this expression here is, it's really, really important. This expression here is a rule for my gradient everywhere. Okay, and that's what this particular unit of work is about. It's a rule for my gradient. All right, and what we say in particular, what if I want to know what the gradient of the line is at the point where x equals to 2? So what I've done so far is I've picked the line that joins 3 and 1, sorry, the line that joins 2 and 1. What if I want to know what the point is there? What is the gradient at x equal to 1 specifically? So what that really means is, if we zoom in on our calculator and just get a lot closer and a lot closer up here to the point where x is equal to 1, what we're saying is h is equal to small values. So if I say put h equal to 0.1, my gradient m would be equal to, well, f of 1.1 minus f of 1 over x2, which is 1.1 minus 1, which is equal to, well, we've got to work out what 1.1 squared is now. What's f of 1.1? Let's have a quick check on my CAS. 1.1 times 1.1 equals, should have known that, 1.21 minus 1 over 0.1 gives me 0.21 over 0.1, which is equal to 2.1. So you could see that if I had h up here, h was equal to 2, my gradient was 4, the line joining the points. If h was equal to 1, the gradient was 3. If h is equal to 0.1, well, the gradient is 2.1. And if what we'll in fact find, if we come back over to here, if we say the limit as h approaches 0, in other words, as h gets really small, of 2a plus h, well, if h is a really small number, like 0.0000, well, that answer just becomes 2a. So that's what the gradient of that line becomes, 2a. All right, and so that gradient, okay, it's given a couple of different names. So because we're dealing with the line y equals x squared, we're saying the gradient of the line at any point on x is equal to 2x, or at any point a. So it doesn't matter whether a is 1 or 2 or 3 or 6. That expression there, this expression here, is the gradient at any point. All right. Now, we call that the rate of change, the instantaneous rate of change. So up here, okay, and we're going through a lot, we worked out the rise over run, and that was my average. So that line that joins from 1 to 3, that gradient is just the average change between x equal to 1 and x equal to 3. Okay, so that's my average rate of change. If I want to know what the change is at a specific point, at the instantaneous, it's called, it's given a special name, and it's called the derivative. So the instantaneous rate of change for my y equals x squared graph is equal to 2x, and 2x is referred to as the derivative of x squared. All right, so that term, that derivative of x squared, is 2x, and we use some different notation. And at this point in time, we're going to talk about the derivative as really being the gradient function, because what is absolutely critical is that when we hear the term derivative, you've got to think to yourself, oh, he's just talking about the gradient of the function. Okay, so If we have a look at this example here, by considering the gradient of the chord that joins the points P and Q, find the gradient of y equals x squared minus 2x at the point Q with coordinates 3, 3. So again, the gradient, let's just make a bit of space, might do it in a couple of. So the gradient y equals y2 minus y1 over x2 minus x1, yeah, which is the same as f of, well, what are our points? So we can see here, I'm going to start with the point 3. So I'm going to call x equal to 3, and then x1 equal to 3, and x2 equal to 3 plus a little bit, okay, which is what I've got there. X is equal to 3, and I want to consider another point P, 3 plus a little bit more. All right, so my notation means y2 is going to be equal to f of x plus h minus f of x over x plus h minus x. So that's just y2, y1, x2, x1. So what are these values equal? So first things first, let's go here. F of x plus h is equal to, substitute x plus h into the rule, x plus h squared minus 2 times x plus h, and f of x is simply equal to x squared minus 2x. So let's put that into our rule. Let's use green for this function here. So we know the gradient is equal to f of x plus h minus f of x over, well, x plus h is 3 plus h minus 3. All right. So m is equal to, expand this expression here. So I'm going to put m is equal to x squared plus 2xh plus h squared minus 2x minus 2h, subtract x squared minus 2x, which is the f of x, all over, well, 3 minus 3 is 0. All I get left with is a h on the bottom. The gradient m is equal to, let's go, I've got an x squared minus x squared, and I've got negative 2x, minus or minus is plus 2x, they cancel, and that'll happen every time. I'm going to end up with 2xh plus h squared minus 2h all over h. So m is equal to, let's take h out the front, I get 2x plus h minus 2 over h, they cancel. So I get m is equal to 2x minus 2 plus h. So then what we do, as h gets close to 0, my gradient m is equal to 2x minus 2. That's the rule for my rate of change. Okay. Find the gradient at the point Q with coordinates 3, 3. So specifically now, at x equal to 3, my gradient m is equal to 2 times 3 minus 2, which is equal to 6 minus 2, which is equal to 4. Okay, so that's what we call the grade. That's the gradient of the line. It's the derivative at that point. It's my instantaneous rate of change at that point. Okay, so two different expressions there. 2x minus 2 is the general derivative, is the rate of change, instant rate of change anywhere. And 4 is the derivative, at x equal to 3. It's the gradient of the curve at x equal to 3. It's the instantaneous rate of change of the curve at x equal to 3. All right? All right, let's have a go at one more. Similar sort of thing. Let's just get ourselves a little bit of... Right, so again, find the gradient of the chord PQ and hence the derivative of x squared plus x. So the gradient of this chord, m, is equal to y2 minus y1 over x2 minus x1, which is equal to, well, there's my x2 value, there's my y2 value, that's my y1, sorry, that's my x1 and then my y1. So we've got y2, which is equal to y2, which is equal to, well, let's just put it in. It's going to be x plus h all squared plus x plus h minus the y1 value, which is x squared plus x, all over y2, which is x plus h, minus x1, which is x. Not too sure what I said. So there's y2, y1, x2, x1. Okay. So the gradient m is equal to, let's expand the top line. I get x squared plus 2xh plus h squared plus x plus h minus the red, so it's minus x squared minus x all over x plus h minus x. So there's y2, y1, x2, x1. So let's just simplify now. M is equal to, so I've got an x squared term cancels with an x squared term. I've got plus x with a minus x, so my x's go. So that leaves me with 2xh plus h squared plus h all over h. So that means m will equal, let's take h out the front, I get 2x plus h plus 1 all over h, cancels off, m is equal to 2x plus 1 plus h. So that expression there, okay, is basically my derivative expression, my rate of change expression, okay? Now, don't forget, I'm interested when h gets really small, that term disappears. So m is equal to 2x plus 1. So I guess more correctly, there's my derivative. That's my rate of change. That's the gradient for that particular function anywhere for any value of x. So for example, what the question say, just find the general answer. If I put x equal to 1, the gradient is equal to 3. So at x equal to 1, which might be about there, the gradient of 3 looks about right for that tangent line, for that line that touches there. If I put x equal to, well, if I put x equal to negative a half, my gradient will equal, well, 2 times negative a half is negative 1 plus 1 is equal to 0. So that point would be there at x equals negative a half. And that horizontal line has a gradient of 0, so that kind of makes sense, okay? So that little expression there in yellow gives me the rule for the gradient everywhere for that particular curve. Okay, and that becomes important because our gradient value will have significance for us as we go through. All right, let's have a look at our next one. By first considering the gradient of the chord from f of x to p of x plus h, f of x plus h for the curve f of x equals x cubed. Find the derivative of x cubed. Okay, so again, it's find the derivative of x cubed. So what do we know? We know that the gradient m is equal to f of x plus h minus f of x, that's y2 minus y1, over x plus h minus x, and they cancel out straight away. So m is equal to, so they're just after the general, so f of x plus h is equal to x plus h all cubed minus f of x, which is just x cubed, over, I'll just put the h there now because that's all that's left. So how good do you remember your expansions? M is equal to x plus h cubed is equal to, in blue, it's equal to x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, so that's the two different functions on the top, all over h. What cancels out here, I've got an x cubed there, oops, that should be an x cubed, minus x cubed because that's f of x. So m is equal to h at the front, 3x squared plus 3xh plus h squared, all over h. So my gradient m is equal to 3x squared plus 3xh plus h squared. Now don't forget, we want to get h, as h gets really small, that will be 0, that will be 0. Therefore I get m is equal to 3x squared. So that's what the gradient is. So the rule for my gradient for the curve y equals x cubed is given to us by 3x squared. So formally we say the derivative of x cubed is 3x squared. Okay, let's just do a little bit of formal limit work. All this notation really means is as h gets really close to 0, which means really if h is 0, what does the expression become? And in this case, if h is 0, the expression becomes 2x squared. In this one, if h is 0, well, there is no h, so I just get left with 5x. In this one here, if I put h equal to 0, I get a 0 on the top and a 0 on the bottom. That means we can do some cancelling. So, as we had been doing before, if I take h out the front, I get 4x squared plus 3h all over h. They cancel. So that expression becomes the limit as h approaches 0, 4x squared plus 3h. And now if h is equal to 0, that term disappears, so I get left with 4x squared. And similar here, if h is equal to 0, I just get left with 3. So that becomes 3. Have a go at those, boys.